Hi students, in this lecture we are going to solve problems on SHM. See question number 36. A uniform plate of mass m stays horizontally and symmetrically on two wheels rotating in opposite directions. The separation between the wheels is L. The friction coefficient between each wheel and the plate is mu. Find the time period of oscillations of the plate if it is slightly displaced along its length and released. This is a question given. See how we are starting the problem. They're asking find time period of oscillations of the plate if it is slightly displaced along its length and released. So first we are focusing on who is providing restoring force for the plate to oscillate. I am repeating, who is providing restoring force for the plate to make oscillations. Then we are focusing how many forces acting on the plate. You can see here number of forces acting on plate. I am making here free body diagram for the plate. Number of forces acting mg downwards. So mg downwards. Now we have contact with each wheel. Normal reaction upwards. Normal reaction upwards. Initially, the plate was placed symmetrically. Therefore, normal reactions will be same. I'm calling one of them N1 and second one N2. Initially, plate was kept symmetrically. Therefore, N1 equal to N2. And here we are having at the contact one more force, that is a friction. Frictional force we have to take at each contact, which is in the plane of the plate, like this. When normal reactions are same, limiting values are same. I can say F1 equal to mu into N1, F2 equal to mu into N2. When N1 equal to N2, limiting values are same. That means net force along horizontal is zero. But when we displace the plate, normal reactions are not same. Let us take displace the plate right side. Then normal reaction will be more. That means we can say N2 value is more. When N2 is more, F2 value is more. That means F2 minus F1 provides a restoring force. We can say solution next page. So first I'm writing N1 plus N2 equal to mg. Because along vertical on the plate net force must be 0. N1 plus N2 equal to mg. Next, plate is having only translatory motion. Therefore, torque must be 0. So we are taking net torque should be 0 about center of mass. So I have taken here N1 into. See initially what happened. Plate was kept symmetrically. Therefore, distance from both wheels same L by 2, L by 2. But now displaced X right side. Therefore, distance becomes now from the left end, it is L by 2 plus X. Distance of center of mass will be L by 2 plus X. And this becomes L by 2 minus X from the right end. That's why N1 into L by 2 plus X equal to N2 into L by 2 plus X. That means because of N1, about center of mass, torque is clockwise. This is a clockwise torque. Because of N2, torque is anti-clockwise. So they are equal in magnitudes, directions opposite. So net torque equal to 0. Equation 1, equation 2. So we have two unknowns, N1 and 2, and two equations. So solving 1 and 2, we get N1 and N2. So N1 is mg by L into L by 2 minus x, N2 mg by L into L by 2 plus x. So after having N1 and 2, now we calculate restoring force. That is F2 minus F1. So take mu into N2 minus N1. Substitute values in this. We are getting F equal to 2 mu mg by L into x. So it is of the form F equal to K into x. If you want to write here minus, that means if you want to write in vector form, restoring force is left side, but displacement is right side. So F is negative, X is positive. We can take minus. Okay. That means in the place of K, we have 2 mu mg by L. Right. I'm repeating, in the place of K, it is 2 mu mg by L. Now, general formula for tampere is T equal to 2 pi root m by K. Right. So now in the place of K, writing now 2 mu mg by L. Then we get this is the answer. Okay. So we are focusing on what is restoring force. Okay. And this question is taken from H.C. Verma. See next one. And this question also from H.C. Verma. See the question. Two small balls, each of mass m, are connected by a light rigid rod of length L. So this is the rigid rod. The system is suspended from its center by a thin wire of torsional constant K. This is a thin wire. Its a torsional constant is K. Thin wire. The rod is rotated about the wire through an angle theta naught and released. Rotating the rod by some angle. Then what happens is wire gets twisted. I am repeating. When we rotate the rod, wire gets twisted. Okay. Now he's asking, find the tension in the rod. Find tension in the rod as the system passes through the mean position. Tension in the rod. Okay. See how we are starting the problem. Once we release the rod, you can see in the string, there is a twist in the string. Because of the twist in the wire, there is now restoring torque. And that is given by, you can see your solution. Because of the twist in the wire, torque is given by that torsional constant into theta. That is now restoring torque. Because of that torque, the rod rotates back. Because of that torque, the rod rotates back. When rod is rotating, the balls are following circular path. I am repeating. When rod is rotating, the balls are following circular path. So now we have to focus who is providing who is providing centripetal force for these balls to follow circular path. And one more thing we have to focus, motion of the balls is confined to only horizontal plane. I am repeating, motion of the balls is confined to horizontal plane. That means along vertical, net force on the balls must be zero, right? Then what we are saying is here, one component of the tension in the rod, one component of the tension in the rod is balancing. I can say here I'm drawing, you can see next page. Yeah, let us take F is tension by the rod or tension the rod. Let us take horizontal as x-axis and up as y-axis. So one component of the rod's tension has to balance mg. That is y component of rod's tension balancing mg. X component of rod's tension providing centripetal force because balls are following now circular path, right? So centripetal force that is equal to mass into R equal to L by 2 omega square. Okay. So we got the value of F5. We require Fx. If Fx is known, then rod's tension is given as F equal to square root of Fx square plus Fy square. Right. Okay. Now to find Fx, we require omega square. Okay. To find omega square, we are using now energy equation. When rod is rotated, wire gets twisted. Because of this twist, potential energy is stored in the wire. I am repeating. Because of the twist in the wire, potential energy is stored in the wire. When rod passes through mean position, this potential energy completely converts into kinetic energy for the balls. So energy equation is, we can see energy equation half k theta naught square. So it is just like half k x square in case of a spring. X is a compression or elongation. Now same kind of expression now for the string also half k theta naught square, that is a potential energy, that is converting into kinetic energy for both the balls. So I have taken here half 5 omega square for one ball. Since for two balls it is into 2. So from this we are getting omega square value. So in this I value how much means? I value distance of each ball from center of mass, that is L by 2. So it is m into L by 2 whole square. Taking this value, we substitute omega square here. We get the value of, it is Fx, right? Then tension is square of Fx plus square of Fy. That is tension. And here, if you observe carefully, tension is not along the length of the rod. I will draw a diagram here. If rod is like this, and this is one ball, on the ball, one is Fx like this, and one is Fy like this. So rod's tension is not along the rod length, it is making some angle. So conclusion is rod's tension need not be along the rod length. If you see in case of strings, tension must be along the string length. But force in the rod, it need not be along the rod length. Okay. That is one important conclusion that we can draw from here. Right. See next problem. Right. Read the question carefully. A uniform plank of mass m free to move in the horizontal direction and is placed at the top of a solid cylinder of mass 2m and radius r. The plank is attached to a fixed wall by means of a light spring of spring constant K. There is no slipping between the cylinder and the plank and between the cylinder and the ground. Find the angular frequency of small oscillations of the system. Right. So here what we can do is Planck executes simple harmonic motion, and here what we call this is given cylinder, right? This also executes. Means when cylinder is rolling, axis of the cylinder executes a simple harmonic motion. I am repeating. Here Planck executes simple harmonic motion. At the same time, axis of the cylinder also executes a simple harmonic motion. Okay, right. Let us see how we are starting the problem. So we are solving this in two methods. One is using force and torque. Second, by using energy method. Okay. First is the sentence what is given here. Let the cylinder be rolled clockwise and the axis has moved x distance. I am making diagram here. Cylinder axis has moved distance x. If it moves distance x, Planck moves distance 2x. Because it is a contact point having velocity twice the velocity of axis of cylinder. I am repeating. There's a point of contact having twice the velocity of axis of the cylinder. That's why there's a Planck moves 2x. That means the spring compresses by 2x. Now see force equation for Planck. By the spring on the plank, I am drawing here. By the spring on the plank forces, it is now 2kx. I think I have written here only kx. Make correction here. It is 2kx. Okay. And assume friction is now right side. Assume friction is right side. This is a completely our choice. I have taken it is right side. So net force on the plank, that is 2kx minus f, that is equal to m into a. Equation 1. Now coming to the cylinder, it is now rolling, and this rolling can be taken as a pure rotation about one axis, which is known as instantaneous axis of rotation. What is it? Instantaneous axis of rotation. Let us call this as a point P. Then see, I am taking torque equation for the cylinder about P. That is F into 2R, because of frictional force acting at the topmost point, that is direction left side. So torque will be, it is anti-clockwise. See, it is rotating clockwise, but torque is anti-clockwise. Means having a restoring torque. Okay. So equation is F into 2R, because distance from point P is 2R, equal to moment of inertia about point P into alpha. That is equal to, see what is I value. I am writing here I value about P. About P I value, mass is given 2m, so it is a 2m into r square by 2 plus 2m into r square. Using parallax theorem, that is equal to 3m r square. That is what we have taken here. Right? 3mr square into alpha. So from this f equal to 3mr alpha by 2. Substitute this value or do one thing. First take relation between a and alpha. Okay. So a equal to 2r into alpha. Where a is now acceleration of the plant. A equal to r into alpha. Substitute this in equation 2 in the place of alpha. In the place of alpha, a by 2r. So a by 2r means we get f equal to 3ma by 4. Now substitute this 3 in equation 1. In equation 1, I am making calculation here. 2kx is equal to, I am taking ma common, 1 plus in the place of f. 3ma by 4 means it is 3 by 4. It is now 1 plus, sorry, 4 plus 3, 7. So 7ma by 4. That is equal to 2k into x. Okay. That is equal to 2k into x. So from this, what is a value? A value. So here I should write here a value 4k by 7m into 2x, not x, it is into 2x. Into 2x. I am leaving only like 2x only. The reason is that here 2x itself is a displacement of the plank. See carefully. Plank has moved by a distance of 2x. So 2x itself is displacement of the plank. So 2x is now displacement. Therefore, 4k by 7m becomes force constant. Right? That means it is of the form A equal to minus omega square into x. A equal to minus omega square. In this place, x is nothing but 2x displacement. Okay. Then we get time period. See now same thing by using energy method. So this is more simple. Energy. See how we are writing energy. Coming to energy. For the spring, compression is 2x. So half k 2x whole square. This is kinetic energy for the cylinder. I'm writing half into its mass 2m into v square into 1 plus 1 by 2. So first part corresponding to translation, second part corresponding to rotation. So translation plus rotation. Okay. Right. Plus half into m into 2v whole square. This is the kinetic energy for the Planck. Planck velocity is 2v. Okay. Now differentiate this, make it equal to 0. Then we are going to get A equal to. But remember in this one, why we have taken here x. And there, why we have taken 2x. So students may get a confusion here. So here, x is a displacement of the axis of the cylinder, right? Because you can see here in the sentence, axis of the cylinder moves by distance x. Okay, that's why here we got x, right? Like this, we can solve in both methods. Let us see next problem. Right. See the question carefully. A cylinder of mass m and radius r is placed on an inclined plane. One end of a massless spring of a spring constant K is fixed to the top of the cylinder and the other end is fixed to the inclined plane. The cylinder rolls on inclined plane without slipping. Find a period of a small oscillations of the cylinder. This is the question given. I will make a diagram for the question first. It is a cylinder, taking as solid cylinder, inclined plane. Suppose angle is a theta. This is now cylinder. Spring is connected to top of the cylinder, right? So whenever we want to calculate in case of spring time period, there we can neglect gravity. So which makes a calculation simple. So if you neglect gravity, there is no elongation, no compression in mean position. First thing. Let us take cylinder is moving down, means axis of cylinder moves down x. Cylinder is now rolling. Suppose axis of the cylinder comes down by x. Then spring elongates by 2x. Now write here energy equation. Half k. Spring elongates by 2x. So I have taken 2x whole square plus kinetic energy for cylinder half mv square into 1 plus 1 by 2. So first one for translation, second one for rotation. Now this total energy must be constant. Remember, we are taking here no gravity. That's why there is no gravitational potential energy, right? Now differentiate this. Half into k into derivative of 2x square, right? And remaining part. After making calculation, we got here a equal to minus 8k by 3m into x. So it is of the form a equal to minus omega square into x. Okay. Remember here theta is not given. Its meaning is that time period is not depending on angle of inclination. Suppose you are given same problem, it is like on a horizontal surface and it is now rolling on that surface like this. Even in this problem also, time period will be same. Okay, right.